So in the previous outing, we learned about what is friction, and I told you about the static friction and the maximum static frictional force, which when is equal to the applied force, okay, in the limiting case of friction, when there is an impending motion, then we have the mu s, that is the coefficient of friction in the static condition. The moment the force is effective in moving the body, naturally there will be an initial acceleration that may continue, and the speed of the body with which it slides relatively over the floor with which it is in contact, that is achieved, then readily at that instant of time the frictional force drops. And we describe this frictional force as the kinetic friction or dynamic friction. And dynamic friction is always less than the limiting friction, mu s maximum. Okay, so the force is always proportional to the normal reaction, and so in either case we find that the forces are proportional, and then if I plot it as a function of normal force, okay, and one of the things that we discussed was the beautiful concept that is associated with it, that if this is the block like this and I'm applying the force to push it, I'll get the frictional force on the other direction. So this book has, for example, this block has a fixed mass m, okay, and but if I put the block like this, or if I put the block like this, then the area of contact, it changes. But we find that in all the cases the same relationship, the same experimental result is obtained, which shows that the frictional forces and the frictional constants are independent of the area of the contact between the two surfaces. To make the things clearer, I am just taking a few examples and will explain many other things associated with the problem solving. For example, in the first example, I am taking a box on the floor of an accelerating train. Because if the train is not accelerating, then because of the static friction between the two surfaces, the body will remain as such. It will not be affected, its motion will not be affected if the train, for example, this is the floor of the train, this is the compartment of a train, and the train is moving with a constant velocity. The motion is in this direction, okay, but I'm just showing that the motion in this direction, and the relative motion between the two of them, the box and the floor of the train, is 0. However, the train may move with the train velocity which is not equal to 0 and a an acceleration associated with it which is not equal to 0. So what will happen is, if this floor were frictionless and our train was moving in this direction with a certain acceleration, then naturally in reaction to that kind of a motion, my mass, my box will move in the opposite direction, okay, and it may go back to the back of the compartment where it is kept if the floor has no other hindrances, resistances, etc. for the movement of the box. Then the box will go to the rear end of the train compartment and it will go and hit the wall over there. Now, with this very simple thing that I have just described, and wherein I have taken the value of G as 10 meter per second square. Normally I will take this because it helps in calculation. Then you can see that one of the forces which is acting on this mass, the box, is in the downward direction, which I say mg due to the earth, and there will be a reaction force which is equal to the normal n. Okay, so how do we solve this? How do we find what is required is what is the acceleration for which the box will keep on start slipping, moving due to the acceleration of the train. So I can write a very simple this thing, that the mass into acceleration, which is the force, mass into acceleration, I am using Newton's second law, this is equal to Fs, the force of static friction under the condition that it has just started moving. And we know that this Fs force is smaller than or equal to, okay, the force mu s into n, where mu s is the limiting friction coefficient. It's very simple, okay, and so that I can write that Fs is smaller than, Fs is smaller than or equal to, for the value n I can write it as equal to, so this is equal to mu into mg, mu into mg, which if of course the value of mu s is also given to us. This is equal to 0.20 for example, and this you know is pure number, it has no unit. This is a pure number, so this must be, if I substitute the values, this must be smaller than or equal to mu mg, mu smg, mu smg, so it is equal to 0.20, 0.20, the accuracy is up to the second digit, and then mg, which is sorry, I have to write the acceleration. I have to write the acceleration. That means the acceleration is this divided by this value divided by m, so is mu s mg divided by m. So the acceleration is, I can write it here, that the acceleration a is therefore smaller than, equal to m, and m will cancel. So this is a very interesting thing, that this acceleration which we are going to calculate, it is independent of the mass of the body. Even if the box is lying like that, or if you make a child sit on the box, it's not going to make any difference. And so if I calculate this, it will be less than equal to mu s is 0.2 to 0, I write it again, into 10 meter per second square, and this is smaller than equal to 2.0 meter per second square. So you can see that in this very simple problem of a box on the floor of an accelerating train, we see that if the acceleration of the train is less than or equal to just when it is 2 meter per second square, that the box starts moving. Okay. Then we have a second example. The second example is that of an inclined plane. I have shown you this is the horizontal plane, and then there is a plane which we can raise like this on a hinge. Raise gradually, okay, on a hinge. What is a hinge? Hinge is an axis on which the plane can be moved. So we can show the hinge like this. We can show the hinge like this if the hinge is coming out in our direction, or like this if you observe it to be away from us. But anyway, this is not an occasion to talk about the hinge. The only thing is that my inclined plane OB can be raised, and there is a box. Here in this situation we have a box of mass 4 kilogram. We will see if this value of the mass 4 kilogram is of relevance or not. So what I find is that there is a geometry associated with it. We have to draw this clearly, the box, and we see that the center of the mass of the box, if I take it here, then there is a gravitational pull which is mg, and you can see that the surface in contact is here, so there will be a normal force which is perpendicular to the surface and normal to the surface. It's what we call normal. And when this angle is theta, whatever value, we'll find out, okay, later on, that this body will start slipping. So we want to know what is the angle theta at which the body starts slipping. The static friction and the force of friction is in this direction, and the force that is applied parallel to it is like this. You can see this force mg I can resolve, because the geometry says that this angle is also equal to theta. Geometry says that this angle is also equal to theta. So then I resolve in this direction, and it comes out to be equal to mg, the force that we have, the vector value, into cos of theta. And as I told you before, that the resolved part in a perpendicular direction over here, because this angle is theta, so this angle becomes equal to pi by 2 minus theta. So by the definition of resolved parts, the resolved part in this direction is equal to mg into cos of pi by 2 minus theta, which is nothing but sine theta. So I have a mg sine theta component, mg cos theta component. And now we can write the equations. I'll be writing it just now, but we can write the equations equating mg cos theta to n and equating mg sin theta to fs. So let's do it. So dealing with the problem further, from here I have to find out what is required is what is the value of mu s, the limiting friction or the RD static friction, when the body which is still now at a velocity of 0 and while we are bringing this up, this plank on which the body exists, when the value of the theta is increased from 0 slowly and gradually, the value of this theta is also increasing to mg sin theta will also increase, and fs, the force of friction, also keeps on increasing. In the limiting case, in the limiting friction, what you will find is that the mg sin theta will become equal to fs. Okay, the force of static friction on it. And as it appears here, because this force mg is resolved into mg cos of theta and this is balancing the normal force over here, so I can write another equation, mg cos of theta is equal to n. Now the system starts sliding on this couple of surfaces, the surface of the box and the surface of the incline. At that moment, when theta becomes equal to theta maximum, which has been described like tan theta is equal to 0.27, or even this theta is taken as equal to 15 degrees, okay, then what we find is that fs maximum, this is equal to the coefficient of static friction mu s into the normal force mu s into n. So if I divide this equation by this equation, so naturally what we get is mg cancels out, sin theta max divided by cos theta max, which is tan theta max, and this turns out to be equal to fs divided by n. If I substitute the value of fs as has been described here in this equation, if I put this value over here, and you see that n and n, they cancel out. N and n, they cancel out. So what we get is that tan theta maximum is equal to mu s. Now it has been described in the problem that theta max is equal to tan inverse of mu s, and this is approximately is given as 15 degrees. So when I try to find out the value of mu s, I take a tangent on this side, tangent on this side. So tan into tan inverse, that cancel out, and mu s becomes equal to tan theta maximum, and this is 0.27. Look here, there is something which we observe is that in determining this system or in discussing this system, the value of m again is immaterial. In finding the value of mu s, what is material is the nature of the surface of the block in contact with the surface of the incline. That is important. The mass, if it increases, then of course this value mg increases, mg cos theta increases, mg sin theta increases, but this theta, which turns out to be theta maximum, and the motion starts working. So this is another example in which I have taken the nuances of the frictional forces, and then we move on to another situation in which there is a uh, there is an string attached to a mass, as also to a trolley which we want to move on a surface. Okay. So after these two examples that I have taken, in first case where there was a box on a horizontal surface, and the second in which there was an incline to a horizontal surface, there was a plank, and we tried to discuss that problem, but right now it's a very interesting thing. And the interesting thing is that I have a surface, a rigid surface, okay, a rigid plane, and on this plane I have a trolley. I have a trolley, to which there is a string has been tied, and it goes over a pulley, a smooth pulley, no friction, no nothing, pulley, over which the string passes over, and a small weight of 3 kg is tied to it. The string is inextensible. The string is inextensible. There will be another occasion when we will discuss. Right now, tensible, bill. Inextensible string is there, but this string, while this is happening, is under the condition of a tension. And I told you that tension in any part of this string, for example, if I take just now a point over here, then remember that the string experiences a tension in both directions. This direction, also in this direction. Okay. Similarly, if there is a point over here, then the string, again a stretched string which is inextensible, which is under tension. Tension is a beautiful concept, but tension is we are not able to explain tension normally, but I have explained tension to you. So there is a state of tension, and this is also a state of tension. Now you can ask a question, and you are justified. Why is the tension here in this direction, and why is the tension here in this direction? The reason is that we are looking at, in the first instance, the motion of this body. When the motion of this body is there, then there is a force of friction in the opposite direction to the motion, and which I have shown for this mass, this weight, the mass having 20 kg of the pulley that we have, then we see that I have made a diagram which is called free force diagram, which explains as to what is going to happen to this body. I told you, if you remember, that Newton opined, he thought, and because while he was solving problems, not very simple problems like that, but tricky problems, also associated with the British army requirement in those times, that Newton had trouble in the application of his laws of motion to the practical situation that were there. And I told you that Newton said that the state of a body is determined by the forces acting on the body. So on this body, how many forces are acting? One is the force of tension of the string, and other is the force of kinetic friction while it is moving. Because the trolley will be moving, therefore we take the kinetic friction. Then what we have, the other body, this is also moving in a vertical direction. Now to this body has a mass of 3 kilograms. So that means that the weight of the body or the force on the body is equal to 3 into 10 is equal to 30 newtons. And naturally, because this body is going down, okay, so we have the state of a body is that this body is moving downward in this direction. I'm not talking about the velocity of the two bodies will be the same, but the major thing is that the associated acceleration, which must be in this direction here, and the associated acceleration in this case also will be in the same direction, yani like this. If you look at the string under tension, then you find that this is accelerating, so this must also accelerate in the downward direction. And we have the acceleration here, we have the acceleration here, and we have a velocity over here. There will be a velocity over here. And now, to look into the problem, look into the example. Now we can write the equations from these relations. So, the mass over here, the normal reaction is 200 kilograms over here, and I can write this as one moment. Firstly, and yes, so I can write the equation as like this, that 30 Newton minus T, the first equation from here for this body, 30 newtons minus capital T, the tension in it, is equal to, this is a 3 kilogram body, so we are just talking about this body over here, so this is 3 into A. The acceleration that will be there is equal to A. So 30, of course, the units everywhere will be the same. The units are in terms of newtons in all cases. And in the second case, I have T over here minus what? Fk, the kinetic friction. The kinetic frictional force, this is equal to 20 is the mass of it, and into A. So you get these two equations, wherein I can write that Fk I can write by definition, which we have, of mu k into the kinetic friction, mu k into n. And mu k, the kinetic friction, is described as 0.04. I forgot to write that. Mu kinetic here is equal to 0.04. It could be any value, it doesn't matter what the value is. You can always make the calculations in like this. Of course, n is equal to what? Here n is equal to 20 into g. So 20 into 10 is equal to 200 newtons, but because I'm writing n over here, so I will write this newtons. Remember, it is not only in the case of the newtons, but any other unit, that if the unit is represented by a capital letter, the name of the scientist comes out with a small cap letter. Okay, so I'm writing it as 200 newtons. Okay, so Fk will turn out to be equal to, so my Fk, therefore Fk will turn out to be equal to 0.04, very easy, into 200, which if you multiply readily you must be able to do so. 0 0, and this becomes here, it becomes 4 to the 8 what newtons. Okay, so this turns out to be 8 newtons. So therefore, substituting in any of these two equations that we have written, for example, if I write here, okay, I can say that 30 minus 8 in the first equation, 30 minus 8 will give us this plus this, 23, because t's will cancel out, 23 into a, which gives us the value of a equal to 22 divided by 23 meter per second square. A is equal to 22 divided by 23 meter per second square okay, which of course we can calculate as equal to 27.1 meter per second. I'm sorry. Then we calculate the value of t, and the value of t turns out to be equal to, finally if we substitute this value here, the value of t we can find as equal to 27.1 Newton. I leave it to you to substitute and calculate. This is 27.1 of course newtons. So I can write this and find out the tension in this case. Okay, look here. Now finally I have received the things, we have obtained it, the tension. It does depend upon what these forces are. Okay, what is the mass of this body and what is the mass of this body, and naturally if the mass of this body is more, then in that case the acceleration, to me it appears it must be more. It is for you to check if the acceleration, if you change the data from 3 kilogram to say 4 kilogram, 6 kilogram, like that, and you will obtain the results of the acceleration, etc. associated with this example. So this example gives us an insight into what are the properties of the string. The string is not extensible. We'll talk about that. If it is elastic or non-elastic or what, etc., when the occasion comes. But right now we leave you here. We suggest that any book that you have, you may have many more questions on the inclined plane system, on a trolley system, and 2 trolleys or whatever, and sometimes there are many pulleys, etc., so you can combine all those things, make it complicated, make it complex, but if you stick to your basics, you can solve any kind of problem. If you have any problems, then as I told you last time, you can go to the comment section, you can register your problems over there, and I will try to address them, and next time when we are meeting, I will tell you about the rolling friction and what is the beauty of the rolling friction and how this rolling friction has been a boon to us in the form of what we call a wheel. So we'll not rediscover the wheel, but we'll discuss the wheel in the next lecture, which is also a part of friction. So I have enjoyed talking to you. Hopefully you have enjoyed this lecture also. And please write in your comments and discuss it with the comments forum in your the notes that we have on it. Okay, thank you very much.